In this video, we will be discussing what is sample rate and bit depth. Now, you won't exactly get into a lot of details about digital theory. We'll do that when we're learning audio engineering, but I just wanted to give you guys a small basic introduction to what is sample rate and what is bit depth, because that is the main setting that we have to choose whenever we are exporting audio. Now, whenever we are recording any kind of audio, it comprises of mainly two signals. One is going to be the frequency response and another is going to be the amplitude. Now here I've got a sine wave. The sine wave, this crest, this is basically the line of 0. And from this line of 0, we have the positive polarity on top and the negative polarity on the bottom. And this right here, from this 0 to the crest, which is the peak, highest peak of this signal, it is going to be called as the amplitude. And the same thing applies here from 0 to the negative crest that we have here. That is going to be a trough. Basically, it is going to be called as same amplitude. Now, this is the difference between the crest and this negative point here, the trough, is going to be its total amplitude. Now, for visualization purpose, I'm only using this sine wave. In real life, the audio waveform is going to have like a combination of different frequencies, combination of different loudness levels. So we won't exactly get a sine wave. Sine wave is something that we can only recreate digitally, and we are using it for this visualization. And we are just getting into the theory. The practicality of this is going to depend on what kind of signal we are processing. So that we will look at a little bit later when we're learning effects like the redux effect in Ableton. Now, what this tells us is basically whenever I want to record a certain frequency, right? This sine wave is going to have a certain frequency associated to it, right? So this frequency, to record this, like let's say this is a 60 hertz frequency. So to record a 60 hertz frequency, I need double the sample rate of that. So to record 60 hertz of frequency, I will require to use a sample rate of 120 hertz. Basically, think of your audio, it is being divided into small chunks. You can see these vertical lines. I've used these to represent how, we would divide the audio signal according to the sample rate. Now, this is going to give us an idea of what frequencies are being used, because generally audible frequency spectrum is from 20 hertz to 20 kilohertz, that is 20,000 hertz. Humans can't generally hear the frequencies above that, and we cannot really feel the frequencies below 20 hertz either. So that area between 20 hertz, that bandwidth of 20 hertz to 20,000 hertz, is what we want to also record and replicate. Now, to record 20,000 hertz, we will need a minimum sample rate of 44.1 kilohertz or 44,100 kilohertz. Now, you might say why that is, because the double of 20,000 is going to be 40,000, right? So if we apply additional processing on our signal, generally that adds more harmonics. So say I am adding some kind of saturation to my higher frequencies, that is going to add frequencies beyond 20 kilohertz. Now, even if we are not able to hear it, a lot of times when that signal is generated, it starts reflecting back into our main signal in the form of another audio waveform. And that results in cancellation of sound. So to avoid this kind of cancellation of sound, we generally give us a little bit of headroom so that we can process it, we can add some kind of distortion to it, saturation to it, and it is not going to completely phase our original signal, and we are not going to get any weird sound effects out of this. Now, more on this we will learn when I'm covering oversampling, and all of this stuff is going to be covered later on while we're studying audio engineering. So you will get a better idea then. For now, you just need to understand that this is how we are going to divide the frequency response. We generally divide it into really tiny chunks, and the most basic sample rate that we generally use in our project is going to be 44,100. Now that's just for frequency. What about the loudness, the volume, right? So for volume, we use bit depth. Bit depth is the terminology that we use, and 16 bits is the most basic bit depth that we use. Now, in digital audio, whenever we are converting the main signal into digital signal, our analog signal, the electrical signal into digital signal, it has to be broken down into bit depth and sample rate for the computer to recognize what that audio is. And then when it is playing back, it uses the same information to convert it back from digital to analog sound. That way we can hear it back from our speakers. Now, when I am using bit depth, generally you get 6 decibels of loudness, or you can capture 6 decibels of loudness per bit. So in 16 bit of bit depth, you can get 16 into 6. With higher bit depths, such as 24 bits, 32 bit floats, you can get a much more, you can record a much louder sound. So generally, right now, what I want you guys to listen to keep in mind is, whenever you are recording something, record on higher sample rates and higher bit depths so that you can capture better sound. Although it is arguable that higher sample rates don't actually add that much audible difference in the sound, which is why generally the maximum sample rate that we tend to use is 48,000 hertz, and the maximum bit depth that we generally end up using is 24 bits or 32 bits. Now, in this waveform, let's create a graph. We'll try to figure out how the computer is going to accept this signal and how it's going to convert this into digital format. So computer generally works in zeros and ones, and when it is converting an analog signal or a waveform into a digital file, it does that using quantization. So it tries to create a grid. Again, this is just for visualization purposes. The way it actually happens under the hood is slightly different, and we'll learn that when we're studying audio engineering. But for now, we're going to visualize it this way. Say I have this analog signal, this sine wave, and I want to convert this into a digital format. So I'm going to create a grid using 16 bit of my this thing, bit depth, and sample rate of 44,100. Now you get this squarish pattern. Now what the computer is going to do is, whenever I try to create a digital file out of this, it is going to round off this to the closest grid. It is going to round off this waveform, this information, to the closest grid, whichever grid is closer to it. Okay, and generally this is how it's going to look like. So since this portion of the waveform is closer to this grid, it is going to give me a 1. Then again, this section is in this half of this square, this square grid. So I'm going to again get a 1. Then now this signal is towards this, it's closer to this grid down here, the horizontal one. So we get a 0. And then again, since this is closer, we get a 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, and so on. It'll plot out a graph such as this. And what happens is, after this, it truncates that information. So you can see we had like a clear curve, right? We had like a smooth curve of a sine wave. However, now that curve has changed into something more like a square wave, a very jittery kind of a quantized version of this. Now what happens is, this signal that was outside of this red line is going to get removed completely. And that removal of that signal is called as a truncation error or a quantization error. This creates a subtle kind of distortion. When you go lower than 16 bits, this distortion is even more audible. Now, for the viewing purpose, for the visualization purpose, I've kept this effect like a little bit more exaggerated. This grid is a little bit too big. But generally, when it's happening in the digital realm, this grid is good enough. Like this resolution of 16-bit and 44.1 kilohertz is really good. It is going to give you almost realistic sounding quality. Now, if you want if you want to record louder audio, we'll have to go up with better resolution, right? So we'll move up to 32-bit of resolution and we'll increase the sample rate to 48,000 hertz. Now you get like even finer resolution, right? These block size that we had here, this grid size has become smaller. Therefore, we have even better resolution now. So we should be able to capture more of this audio. So in the end, we get this kind of a waveform, which is giving us more of the original signal than when we had before. So this is the logic behind using higher resolution, which means using higher bit depth and using higher sample rate. For now, just remember this. But one thing I'll warn you is that whenever you exceed a certain amount of sample rate, you are going to get a huge size of your audio wave files. So if I double this 48, I'll get 96 kilohertz, right? 96 kilohertz wave file is going to have a much bigger size than a 48 kilohertz wave file. So if you have limited storage available on your system, or if you're recording on an internal drive in your laptops or your computers, then I would suggest just stick to 48,000, because 48,000 is also a very good sample rate. You don't necessarily need higher sample rates, but if you feel like there is a difference, if you can tell that there is an audible difference between these sample rates, then sure, you can definitely go for it. Now, the practical use of higher sample rates is when we are processing the audio, when we are applying more saturation, more compression to our audio. We're EQing the higher frequencies. We're increasing the number of frequencies on the high end and adding more and more harmonics to it. That's when the higher sample rate is more beneficial. It's more practical to use. Now, the workaround of using a higher sample rate is by using plugins that support oversampling. Oversampling is basically going to multiply this sample rate by the order of 2, 3, 4, 8, and so on. So for now, just keep your project settings as 48,000 hertz and 32 bits, and you should get a very nice sound. Later on, we will study what is oversampling when we're studying saturation and that other sort of stuff, mostly in audio engineering, and that's when it'll clear out some of more problems with oversampling and that sort of stuff. But for now, just keep these settings, and we'll progress slowly as we learn more about mixing, as we get better at processing a signal. That's when you will actually feel the need to hear those higher frequencies. But for now, until we're just producing stuff, just keep your resolution at these settings. I'll see you in the next video.